we will talk about some various issues which will include the ability on how the systems and also the processes actually do have a representation in mathematics, and how a controller actually does control a loop. And there are many different types of processors and controllers, but we'll go through some of the basics. The control loop itself traditionally does have some classical points, and it really starts off with a measurement of the process. So hence it is very important to know what the process actually is. So in other words, very clearly defined rules and also very clearly defined aspects on how to measure the various points. Now, a lot of the errors which come into loops and also are prevalent in the overall instability is based upon the inability of the measurement to actually to reflect what's exactly going on. Okay, so whether it is a feedback or a feed-forward loop, there is also some measurement to be made. What also occurs is that there is a controller which takes that measurement, then through its own operation, its own algorithm, will determine what is the best course of action. So the best course of action is to create some type of reaction to the process, and hence alter either as a response or in prediction of the actual process. Okay, so the process themselves can be actually described in various terms, and what can also be defined as either a steady state model and a transient model, or a intermediate model. So when and what I mean by that is that the steady state model occurs over time on how the system will react over a long period of time. Now, for a short period of time, really defined as the difference when a system actually changes its requirements. In other words, you change the set point or change the output, and the system has to react to it, and it's that reaction which refers to the dynamic response, which then brings in the typical processes that you see here. So whether the system has a purely resistive linear characteristics, whether it has a second order inductive or capacitive characteristic, if it has inertia, whether it be mechanical, thermal, chemical, or process inertia. There is also various points, and there are specific cases where dead time is a specific point that can be measured very clearly, but it points to a very specific case of delay in reaction based upon a impetus. Okay, so for a resistive type of process, it's important to note that yes, there will be a response, and the characteristics that you see here is referred to as a step change. But what happens is that the process itself will eventually come up to speed, but it means that the system does have a very linear relationship from the change of output to the change of the process, and that is why it's referred to as a resistance. In other words, for a small change of output, in other words, small change of a valve, then you will get a change of the process. Okay, such as a flow system. Okay, so the capacitive type is where it has a characteristics of the loop that has some internal storage. Okay, so it has a the ability to store the process and at a set rate, or at a rate determined by the physical characteristics, respond to that process. But it isn't linear, and that's the characteristic. So you see this particular type of aspects known through most of the typical processes that you will see around in process industries. Now, for the capacity or the capacitance to be effective, there are the ability to store the energy or store the material. And for storage of material, there are typical things of processes that include solids, liquids or gas, and or energy, which could be a thermal energy, chemical energy, or process energy. Okay. So for the inertial type, there is a type of reaction between the impetus, in other words, the stimulus, and the reaction, where you will get a inertial flow or inertial resistance initially, and then the system will actually be responding. So there are mathematical modeling of these type of processes, but they usually are around changing or moving of components. So it could be the position of a gantry robot, it could be the inertial movement of a valve, but anyway, there is a resistance to the movement there. Okay, so of a first order process, a typical one is of level control, of which you'll see that you do have flow going into a particular reservoir. The reservoir will directly vary its height, which is what you're trying to view, dependent upon the amount of material coming in. So there's a direct relationship. Flow going in will cause an increase in a linear increase in the height. Okay, and that's assuming that the cross-sectional area of the process is uniform. So that's one of that's why you do have that linear relationship. If the cross-sectional area of the tank was not uniform, in other words, it had a conical tank, such as this one, then its relationship would not be linear. Okay. Now, it also has to be taken into account that the outfeed pipe will also affect the level, and it needs to be put into the equation or the algorithm that is referred to, that it also reduces the effect of the in-feed pipe. You're saying, well, and by doing so, by saying that, you can say that it implies that the level will go down. Okay. When we have a second order response, where you have a storage element, okay, so you have a single tank, but that then feeds into a second tank, which is a storage element, then the equation of its response is no longer linear. It becomes similar to what you see here, and it follows a exponential form. Okay, so and that is because you're putting a second order response into it. Okay, so the form of a second order then follows there. So what occurs is that for optimal operations of your machine, you need to adjust the coefficients of your controller to your physical process, and that is referred to as tuning. Okay, and the one of the most prevalent prevalent controllers and control loops that are industry are what is referred to as a feedback. Now, a feedback is basically a system that will take the measurement of the process, as we mentioned before, and that is typically referred to as the PV, or process variable, that is fed into a controller, which calculates the difference between where it has to be, in other words, its set point, from the process variable, and then gives you a calculated value, which is referred to as the error. That error then has an issue that needs to be resolved. In other words, it needs the whole purpose is the error needs to be minimized, and then there are different different coefficients within the system, which is there to make an algorithm or be very close to the mathematical estimation of the process, and that then drives a physical output device, an actuator, a variable speed drive, which then drives a change in the process. Now, it is the fact of making sure that that change, in other words, that error, which causes a change to the process, which then reacts as part of its change in process variable. If you have a good estimation of that loop, in other words, how the controller reacts, how the output variable alters the process variable, depends, it really influences how the whole system will react to a change. And reaction to that change is measured in terms of errors. Okay, so, and it could be that you have wastages getting up to the desired value, and hence there are various points such as trying to minimize the error of integration, and we'll talk about what that actually means when we have a look at the graphs. So the error that you will see is based upon an oscilloscope or a trend trace of two particular variables. One is the set point shown in the dotted line, and the one is the process variable, which is the actual response. And you can see here that the set point can very cleanly and change within minimal time, with zero time, because it is just a virtual change. It's a parameter change. It could be a change in voltage. It could be a change in current, but it occurs without inertia. Okay, so that immediately it has no no physical limitations to it. It goes straight up to its constant value. Now, what occurs is that then drives the process change through the actuator, but it can't physically change immediate like that. So it has to then go through a recognized response curve, and that's what we see in dark. So the shaded areas are the differences between the two, and the idea of tuning the process, tuning the controller to the process, is the minimization of those errors. Okay. So as we change different processes, you may say, okay, I wish to make it quicker. Then you may have a different reaction curve. Okay, and those typical reaction curves are ones that you need to be familiar with to optimize the actual processes. Okay, so what are the typical types of controller outputs? Okay, there are two types of controller outputs. In other words, as we mentioned that there would be an error, so we have to change the process somehow. And there are two classical methods on how to change the process. You either put a control that will either fully turn on a variable or fully turn off a variable, and that is referred to as on-off control. And the variations in the process to that may, depending upon their inertial characteristics, may smooth out that that modulated wave, that on-off waveform. In other words, referred to as a pulse waveform, and give you a response. Okay. The other type is one that will continually vary the output, and what is referred to as the modulating control. Okay, and there are two different types. So what do they actually mean? So when we have a on-off control, you can see here that, for instance, this is a heater. The heater will then turn on and off. In other words, full type of fuel, maximum amount, down to minimum amount. And that's how it actually is turned on and off. So what the process does in response to that is, for instance, if you had a lossy temperature loop, in other words, a furnace, then the furnace will increase in temperature if there's fuel there, but decrease in temperature due to its losses when the fuel isn't there. So what you do is you increase it for the amount that the fuel is on and decrease it for the amount of fuel that is off. Now, and so what occurs is that you will have some type of oscillation, as you can see here. Now, what will occur is because of the thermal inertia, the thermal mass that the process actually has in its characteristics, the average temperature will be raised. And that's the whole idea, is that the average temperature will be raised based upon how much of the time that the fuel is on or off. In other words, what is the duty cycle? Okay. So modulating control, it varies that slightly in that instead of the output just turning on full flow and minimum down to minimum flow, so you go high limit, low limit, that it will modulate somewhere in between. In other words, it has an analog value that will able to be used to allow it to, instead of going from maximum, somewhere in between maximums. Okay, so that's what a modulating control. So it could be the output could be a plus or minus 10 volt signal, which could go between 0 and 100% of a valve. Okay, so so that's the type of controllers. Now, I mentioned to you that's the type of outputs, I should say. So I mentioned to you that there were already two types of controllers which were classically being used within most process industries, and that is that you had one that predicts what's going to occur and one that reacts to what has occurred. The controller mechanism, or the controller type that predicts what will occur, is referred to as feed-forward control, and it predicts what it will occur based upon some of the inputs that are going into the system, okay, and based upon a mathematical model will actually give you an output that will change the process. So based upon what is known about this particular process, in other words, an algorithmic model, it will, based upon all its inputs, give you a prediction of the control variable. Okay, so that's the process. It predicts what will go on based upon some very complex and also very suited algorithms. Now, the accuracy of this type of control heavily depends on the accuracy of the model plus the measurement of the variables coming in. Okay. So the other type of a system is referred to as the closed loop model, or also referred to as the feedback model. And that is the type of process that we've described many times, and is also quite common in most industries, where the process is actually being measured through a measurement device. So its effect is actually being measured, and hence, if the effect is different to its set point, in other words, it then makes the controller react to react and change an output, which will then change the process. Okay, so whereas feed forward predicts, feedback reacts. And yes, it does have a set of equations or a model that it needs to understand about the process to be able to react effectively, but that is a different set of equations and a different set of models compared to the feed forward. As you can see, that it would be, because you are firstly changing different timings, but also looking at different inputs. Okay. So, what are the models which are within the closed feedback loop? Well, the three classical algorithms that are being used are what is referred to as proportional, integral, and derivative control. So what does that mean? Is that the proportional control allows the system to know how over steady state time it will react. In other words, if you place a output, then you know for a certain ratio, which is referred to as the proportional gain, how the output will respond. Okay. In an integral control, what it says is, okay, if the desired value is never reached, in other words, the error is never zero, then we need to reevaluate it. And that's where the integral control. And the derivative says if the output is changing too much, which causes a response in the process variable too quick, then you have to dampen it down, and that's where the derivative value is in there. So you may have heard of PID, and that's exactly what we are doing. It works off a black box reactive model, and that's where most processes are suited to. Okay. So what they can work independently or in combination, but the idea is that you need proportional, at least proportional change to take at least the steady state value to the correct value. And plus you can also throw a combination of integral and derivative in the particular system, but the proportional is always required. Okay, so so either we'll need to look at the steady state response plus some of the dynamic characteristics as well. Okay, so the feedback controllers are the ones that are most common to place in most industries. Okay, and if we take now a mathematical model, in other words a block model of it, you'll notice that there are they can be referred to or described in terms of inputs and outputs. Okay, so so the idea is that the different systems are able to take in the changes of the values and then put the output to change that point. So you have the set point, which is usually coming from another piece of equipment, a SCADA system, a PLC, etc., even a local operator control. It then measures the value. In other words, it becomes an input, which is referred to as YT, but also it's commonly referred to as the PV, process variable. and it has an output which changes the actuator, the variable speed drive, etc., and that is referred to as the MV. Okay, so we have, it can also be described as a continuous loop, and that's where you see this, and it, whether you start to talk through in the, from the set point, from the process variable, or even from the manipulated variable, it doesn't matter, because you have to go through that one complete loop to actually point. Now, one of the issues that you need to be always aware of, that this emulates and uses the black box model of a process, and it's important to always keep that process in mind. So you're at the, for instance, at the summation point, which is the difference between the set point and the process variable, it has to be in terms of the units of the process. In other words, the flow, the temperature, the position, the weight, whatever that is, has to be in terms of that. Okay, process-centric is another way. So the control root, now what occurs is that particular model that we mentioned earlier relies heavily on a good response, a good clean response between the process variable and also the set point. Okay, there it has to be linear, stable, without time delay. So that's the ideal case, and I can say about 85% of the cases around the world that actually is true. However, some cases that isn't true. For instance, you may see that there is some distortion in the signal from the sensor, which is being pointed in, or there could be some interference or disturbance to the actual process that disrupts that linear relationship. Okay, and that noise can be in two cases, and we'll go through that in a future one. But the controller will try to react to that noise. So whether that noise is real or is just a apparition based upon the electrical signal, etc., that's what we have to determine. Okay. So I mentioned earlier that the PID have three terms: proportional, integral, and derivative term. So there are various ways to describe it, and that is that the system has an instantaneous error, yes, so it gives you the steady state response. Okay, so you know that for if there's an error, then you have to increase the output. That's the proportional term. The integral term looks at the over time, what is the actual error, okay? And if it's sustained over time, then the whole process needs to be reevaluated. Okay. So the derivative basically says, are we actually correcting the value instead of just escalating the value? So if you are, and what that means is that if it is going in the correct, trying to minimize the error, then that is working on the derivative. Or what you tend to do is increase its value so it will actually go towards that. Okay. So there are various variation to the PID controllers, and that is mainly because there could be non-ideal types of processes. So in other words, the process itself may not really suit the algorithm that you've set it for it, and you need to have variations of the algorithm. You shouldn't have to change the process, but the controller needs to be then had a look at on how it will actually need to be modified, its algorithm, to suit the actual process. Okay, so the most classical ways is that you then separate the type of algorithm that is placed within the controller. And the most useful one, or what is referred to as the ideal, is where there isn't any timing discrepancies between the proportional, integral, and derivative control. In other words, they are all active at the same time, which changes, by the way, the three of those have equal effect, equal timed effect on the output change. Okay. Now remember, all you're doing is changing one output. You're changing one actuator. You're changing the variable speed drive. You're changing what? But there's only been one time. So how we're actually changing its signal really depends upon the combination of these three things. So in an ideal form, good linear relationships, good points, you tend to have them all working at the same time. So, but what, and that's the equations that you will see, and it's those which is the proportional gain, and then the various aspects of the integral reset time and the derivative time as well. And that comes up with the final equation, which has to be solved by your controller. Okay. However, in systems that do have a time delay or don't actually have a good interrelationship between the inputs and outputs, you need to then have a slightly different model. So another type of model, which again uses PID, but the derivative control is actually worked on first, and then the proportional and integral control is then put through the algorithm. So we set with a greater weight and a greater impetus how the derivative, in other words, is it actually going in the right direction first? And then we give it in the term. So we then compensate for the that type of value, and these are typically of what you might see in noisy situation or ones that have a lot of instability, and that's the typical equations that you see here. Okay, so there are many different types of controllers that that are available on the market, including standalone controllers, the pluggable controllers, DCS systems, PLCs, and whether you employ them, the loops and the control loops within computing or within PLCs, or even purely in software, you have to be very careful of the reaction times. Okay, both the reaction times of your machinery and also your loops as well. So you can, some of them are also allow it to be in software and PLCs. Okay, and there are many different types of controllers which also give you the additional facility of being able to change the fundamental equations based upon the reaction times that you set for them, or the reaction conditions that you set for them, including things like changing the gain, retuning the process. All of those are available in many different guises. Okay. So they're also, and these are available in through the ElectroMeet software that EIT does offer, and they give you the ability to do simulation of the various characteristics based upon a modeling of a process. Okay. Now, what is some of the tools that you need to set the different modes of the thing? And as I mentioned, there are two types of controllers, on-off or modulating control. And as mentioned earlier, if your process is suitable to tolerate the ability to allow inertial point of the process to go through and really be able to affect the average temperature. In other words, the energy goes in, yes, the temperature will start to go up, plus, as you can see, it isn't a linear relationship. It definitely has the maximum amount of energy can go in, but it doesn't immediately respond. It actually just goes up in a linear fashion, and that's typically what you see with inertia of a system. However, also, if the system is lossy, and hence you can actually go up and down based upon that. So, and this may be suitable for a lot of different processes, temperature being one of the best ones, because it doesn't really matter and doesn't really change the conditions of the machine if the process doesn't really be able to modulate, and that's what we actually have here. Okay, so when we are modulating, it is the typical process that we need to make sure that you have more than just that basic control. Okay. Regarding what can actually go wrong to a process to enable the tuning to be either not optimal or to be made iterative to actually be more conducive to the real process. So the what we'll talk about is first what is referred to as disturbances, and then about offsets. Now, the disturbances that are classically put into a particular either closed loop or open loop feedback system are the ones that are generally not directly related to the two parameters of the set point and the output, but do affect either the stability, the ratio of the output compared to the actual process variable, and also the timing aspects. So they are the definition of what is referred to as disturbances. And disturbances could be as simple as an offset within a valve. So for instance, the valve doesn't open properly or is wastage, to major things such as inlet and outlet flows of a level tank, cracked or broken machinery, or even processes that may have an economic process to optimize. But the idea is that the process is what we are trying to control, and it generally is only one or maybe two parameters, and the variation of that particular parameter is via one particular, usually one or two particular outputs, but it is how those outputs don't either effectively control the process variable through the interference of other parameters which are classified and grouped as inputs, disturbances. So let's have a look at what we mean by that in, say, a feed-forward situation, or even just a normal process. This process actually has as its output a temperature which needs to be controlled, and that is because the next stage of machine will have to have a fairly constant temperature as its input. Okay, so that's the thing. So if we have a look at the process, we note that there are a direct line of fluid through the inlet, through a heating chamber, and then through the output. So as far as the direct relationship of the control, we are able to put in heat energy that then goes into the heating chamber, which heats up the liquid, which then gives you an corresponding temperature. Okay, so the mechanics seem to be fairly clear. However, what the disturbances will do. And it should be noted that when you try to describe this, you need to be able to describe your process first. So your first process is, if I increase my fuel, I will get an increase in temperature. That's basically the basic premise. Now, when we have a look at disturbances, we generally note the disturbance, how it actually affects that relationship. So in other words, if you have the primary relationship of increasing in fuel gives you increasing temperature, and hence decreasing in fuel gives you a decrease in temperature, then we look at each of the disturbances that we can measure to see how it affects it. And the first one is the temperature of the liquid going in. So the liquid going in can either be a high or low temperature. So if the temperature of the liquid going in is high, then that adds to the effect of the fuel. In other words, the base level which it's coming in is higher, so hence you don't need to actually put in the as much fluid, as much fuel. So hence, as to be able to compensate for that, then we need to reduce the amount of fuel. Okay, so increase in the temperature means a decrease in the amount of fuel, and hence a decrease in the amount of temperature going in also dictates that you need to increase the temperature going in. So that way you have a definite relationship between the disturbance and the variable that we need. Now, if we then look at the flow, we note that the flow will either be increased or decreased. So what does the flow do? The flow is the medium that carries the temperature to the outlet, and it could be steam as the final output, and therefore the inlet material could be water. So if we increase the amount of fluid, we need to increase the amount of fuel, because the time by which the time by which the liquid is able to heat up is reduced. So hence we have the opposite relationship. So for instance, if we have an increase in flow, we need an increase in fuel. So hence those two disturbances directly affect the efficiency of the fuel going in. So hence you need to be able to adjust for that. So that's the basic concept of disturbances. Okay, so and what could go wrong? As I said, the fuel pressure varies, the inlet water temperature varies, and the water temperature. Now, I did deliberately omit one, and it is the air that goes into the system, and that is because the air, which is essential to the fire triangle of oxygen, fuel, and ignition, will definitely decrease the thermal capacity of the furnace if you don't have oxygen enough there to actually burn the fuel, and hence you may have oversupplying of the fuel, which could actually create an inefficient thing. So that's how the various points are. Okay, so when we look at those and a slightly different method, we note that the system itself can also be rather large disturbances, and the understanding of a large disturbance comes down to its mathematical model. Okay, so it's all based upon what direct influence the actual disturbance has over the output or of the controlling point. Okay, so now one of the other systems that we need to have a look at is how each of the different events need to be looked at in terms of what the response of the controller is. Okay, so one of the key things is proportional control out of the PID. So what we know that as the proportional control tends to increase, then the gain, the actual response of the output tends to increase. However, there could be slight disturbances, as I mentioned earlier, and it could be things like wastage or slightly incorrect values or based upon the ability for the system to actually resolve down small enough. And those type of things can lead to what is referred to as an offset. So, and the offset is basically the difference between where the set point is and also where the process variable is. So that's one of the other disturbances or inaccuracies that could occur when you're tuning, okay, or when you're doing your process. So what could occur is as we increase the amount of proportional gain, remember the proportional gain will tell you what is the correct rate of the steady state output. Okay, so the higher the proportional gain, the closer it will be to the offset. Okay, and but the idea is that it also may increase the instability of the system. So which purely by increasing the controller's estimate of what the gain is. Remember, the gain is always the difference between the output compared to the change of the process variable. So the change of output to the change of process variable. So if we're driving that process variable, the output harder, then the process variable may react to it. Okay, so, and hence you go into the different equations that you see here, different graphs. Now, one of the other ways to reduce that error is to reevaluate the process at a regular interval, and that is referred to as the integral action. Okay, so, and it has an integration time, which then allows you to add up all the errors based upon the difference between the set point and also the process variable. And if it is too much, in other words, up above acceptable limits, what it will tend to do is then increase the action of the output, and hence try to drive it closer towards the drag it towards the acceptable limit. Okay, in other words, it tries to reduce the offset even further. Okay, and that's the integral action. Okay, now it does require both proportional and integral action to be added. It can't just be integral because it needs to reevaluate the new base point, and then the proportional value will start to move it closer, whereas the integral value will then try to reevaluate it. So you're continually looking at the integration time and then putting the proportional part up again. Okay. Now, what it does in some instance, is that it may cause a lag of 90 degrees. And what that means is that the output would always try to be responsive to a change in the process variable. So the process variable will know its behind. In other words, it's at its minimum value. And then the the output will be reevaluated, and it will hence try to go to its maximum again, and that will cause what is referred to as a phase lag when we look at the different traces. Okay, now the formula based upon that is what you see here, but it's basically that you are trying to do the reevaluation of the equations of the error, okay, and it tends to, if that error is too much over time, then the output will be adjusted accordingly. Okay, so the typical process is what you see here. The system will look at the level coming in, so the level of the tank, based on a input and an output. Okay. If we note that the actual set point is the horizontal line here, then the actual output would be, the actual processed variable would be what you see here. So as we now put that in place, okay, and we reevaluate it, okay. Once we reevaluate it based upon that small error, okay. So once that, instead of it being a large error that you see here initially, it's then reevaluated under that small error, because you've put that integral value in, and hence you tend to have a lot closer in terms of the actual settling offset. Okay. Now it could either be high or low depending upon the majority of the severity, the magnitude of the severity, but also that that the process may become a little bit more dynamic if you do have the and that could actually create instability if the integral period is too short. So if, in other words, it's trying to reevaluate it, even, say, for instance, whilst it's still settling, and that then it becomes an issue of stability. In other words, the integral action, you're saying, well, okay, some is good, why don't you put it really short? Because of the interaction it is while it's still being in the settling point. So ideally, you need to have the integral period roughly around the point of it when it's no integral in there, that it's just after it starts to settle, okay? And then that becomes the your integration period. Okay, so, but I can tell you, in common practice, it is set too quick, and therefore you get instability. Okay, so when we go through the other parts that could go wrong, we tend to look at what are the long-term issues, and that we have a toss-up between the long-term and the short-term issues. The short-term issues of speed, in other words, reaction, and the long-term issues of stability or steady-state control. Okay, so what could cause instability? As I mentioned before, you may have small changes in disturbance, and it could be, as I mentioned before, that it's too much integral action, okay, or not enough derivative action. Now, I said too much integral action, which means that it is reevaluating it too quick. In other words, the integral time is actually too small. So that's one of the causes of instability. Or where the majority of the instability occurs is that the process has a nonlinear or a time-dominant effect, and hence is inherently unstable. Okay, So stability criteria has been used to quantify this effect, and it basically says that if you have an oscillation, which remember is based upon the controller's misinterpretation of the real response, is that you may have the controller and its output at trying to continually respond in almost like a chasing method, okay, where the stability, where you have the output oscillating compared to the process variable, and hence you may have continuous oscillation. In other words, the output is always oscillating because it's continually trying to hunt and also try to respond to the dynamic process variable. Okay, so and that is actually as part of the process. In other words, it is really what is occurring. So, and another plus is that because the feedback signal, the feedback loop relies on a feedback signal, then it could be due to some electronics. In other words, noise-induced electronics, instability of the process variable within the electronics, or it could be due to sampling time. So there could be some issues based upon that. Okay. Plus also the possibility of not having a good process connection. In other words, that there could be vibration in the process connection. There could be slight errors where the sensor isn't really picking up when it's supposed to pick up. So there are some criteria for stability, which is based in mathematics, and the reason for this is the mathematics are the only thing that the controllers can work on. So it's important to note that the loop gain basically allows a concept called the loop gains allows you to measure the critical frequency, and the critical frequency is for where the stability actually allows the system to oscillate. So for that particular value, the gain is that if you don't wish it to be completely oscillating, then it has to be below 1. And the idea is that you need to have a phase shift there as well. So, and it's important to note that the idea of the output variable to continually chasing the process variable is what we're trying to avoid. Okay. So the total the critical frequency. Again, when we try to put the delay or the gain, and that again the gain is the output divided by the proportion of the output divided by the process variable. Then if that is set at 1, below 1, and it is purely a ratio, but it isn't really relating to the KC value, so depending upon the loop frequency, then the oscillations, which can be, the example we'll show in a different presentation, starts to decay. In other words, the oscillations to that step response will start to decay. When the gain of that loop is equal to 1, in other words, the output and the input, the output and the process variable are of equal magnitude, the change of the output is equal to the change of the output, then you'll have this oscillation, continuous oscillation, or instability when it is increasing. Now, you're saying, well, I don't want my process to oscillate, and that is correct, but the idea is that may oscillate, and you need to know how to account for and also adjust for it. Considerations that may be deviant from the from a ideal situation. So what we'll talk about is how speed and stability and robustness actually comes about. And as we mentioned earlier, the causes of instability tend to be whether you have incorrect alignment, whether you have incorrect actions, and also if you have a disturbance that could actually be an issue regarding the dead time, the gain, or the actual control. So I mentioned before that the stability control is dependent upon how the oscillations actually affect from the process, and hence whether there are the ability to oscillate, but that is an undesirable aspect for most particular systems, where you tend to have the ability or the need to reduce the system to make sure that it actually does have a reduction of oscillation, and hence to get to the final value as quick as it can. So we have also mentioned that there were some issues regarding the mathematical criteria, and basically how it actually changes its shift from the process variables to the control variable and or the output, and see how that actually reacts. So it's, in other words, it's the controller trying to chase the process, which if they're diametrically opposed to the values that are coming into them, then they tend to have a shifting of the frequency. So we mentioned that if the standardized gains were greater than 1, then you would have a signal decay. In other words, if it's oscillating, then it would mean that the output was actually allowing the process variable to settle down over time. If the gain was 1, then what you would tend to go is that the output will react in such a manner to contain or maintain the oscillation, where if the gain was greater than 1, then the output would tend to be further on oscillation. In fact, it would be increasing in magnitude. Okay, so now why does all that occur? And the whole point is that each of the parameters in a black box model of a process can really be come down into 3 things, and that is the gain, the dead time, and the time constants. So when we have a look at the model, we would think of it as in terms of a change of input or a change to the actual process. Now, it could be a valve, it could be a variable speed driver, it could be any type of control input that will try to change the process under what it thinks are controlled conditions. Now, yes, it will actually create an outcome, so you will have a proportional change to the input to the process, and it will then give you an output dependent upon the black box relationship between the input and output. Now, as we mentioned earlier, the input and output do have a fixed relationship, and it could be quite as simple as a linear relationship. Percentage in gives you percentage out, or it could be as complex as a multivariate model, which includes time delays, which includes nonlinearities, and various other non-linear processes. So whether the model creates that prime is really dependent upon the parameters. Now, the classical parameters that are being used to describe the relationship from the output, in other words, what we know as the process variable, and the input, or the control variable or manipulated variable, is that model. Okay. And there are, as you may very well know, there are other influences to that particular model, not just the straight relationship between the control input and the output, but also they have other relationships which are referred to as disturbances. Now, the disturbances could increase the efficiency of the input or decrease the efficiency in the input. So what mentioned, the classical case was the feeder or the heater, and we mentioned that the heater could actually have the system relationship, so that if it actually does increase the value, then it would have an increase in the efficiency, okay, and decrease the efficiency if the opposite occurred. So, and that could include, from the previous point, the feed flow in, or the temperature of the particular point. Okay, so so just to go through some of the relationships and to determine some of the nomenclature. The first point is what is required of the process, and that is referred to as the set point. Now, the set point itself could be looked at in terms of whether it has a value which is set by a external system, such as a DCS system or a PLC system or another unit. Okay, the set point then is the desired value for which the parameter, which is the actual parameter, is set. Okay, the manipulated parameter is the value or the point by which the system actually has to change the value. In other words, it's the percentage change of the actuator, and it could include the change of a valve, the change of variable speed drive, or various other points. But it's the change of the input to the process. So the other part is the other disturbances which upset or can change or influence the relationship between the manipulated parameter, in other words, the valve's point, compared to the process variable, and they are the disturbances. Now, the disturbances are the main part that will actually be able to change the system to make sure that it better follows the system. So the issues are so you have to look at it in terms of what the process variable will actually go through. So the now we mentioned that there is a direct relationship between, or a mathematical relationship between the process variable and its input to the process, in other words, what we refer to as the manipulated variable or the output of the actuator. And it has a black box relationship, and that black box relationship is actually defined in three parameters. What is referred to as the process gain, in other words, the difference, the mathematical difference between, or the ratio between how much input you would need to put to get a determined output, or the sensitivity. The response from the time that you actually change the input to a reflective output, and the delay of that particular point. So there is a lag or response, and also the lag time or the lead time or the response time would be the how long the system will finally get to its final value, in other words, its settling time or response time. But there is also another parameter which determines or can be viewed by its graph of the time before anything occurs in the background. Okay, so that basically is saying that if the settling time to get to its final destination is the response and the lag time. However, the time before it actually gives you any change is the dead time. Okay, so we also said that the process gain is equal to the ratio of the process variable compared to the manipulated variable. That's quite a well-known issue. So when we look at that particular value, and the value of that will determine if the actual part or that is put into a say, for instance, a controller is either overestimating the physical process or underestimating the physical process, then we actually look at the loop stability. So what does that mean? Well, we already know that the mathematical constants within a controller may or may not reflect the dynamic or the steady state conditions of the actual process. In other words, the process itself may be overestimated in its calculations in the controller or underestimated. So hence you may put the controller is expecting a certain rate of response. If it doesn't get that rate of response, then it will try to increase its output until it gets that rate of response. And hence, if it does so, it could create a overshoot as far as the output is concerned, and hence we have the instability occurring. Okay, so that's the points. Okay, now another point that I wish to just go through is the response time and the dead time. Okay, now the response time, which we'll go in further detail, is the rise time of the actual process until it comes up to the steady state, and the dead time is, as I mentioned earlier, the time by which, if you were tracing the set point and graphing it against the response, the process variable, it was the time that it would actually start to give a useful value. Now, Now, another term that is also important to the stability and also the accuracy of any loop is what is referred to as the process noise. Now, the process noise is defined by two particular aspects. And the process noise is really a deviation from the pure signal that is coming from the actual process. So, and it tends to be the analog signal that's coming from the process tends to be fairly slow moving, which basically means that most physical processes won't react that quickly. Okay? You'll have inertia, you'll have momentum, you'll have resistance, you'll have inertial characteristics, so that the actual signal moves fairly slowly, and that's the type of thing that you would see here. Okay, so that's what you would expect if you were looking at, say, an oscilloscope and looking at the type of waveform coming from something like a temperature sensor or a process sensor. It would come a fairly slow-moving reaction. Okay, something like possibly a slow-moving DC. Now, on top of that, what you tend to see is in what is referred to as electrically noisy situation is a higher frequency signal put on top of it. Now, it is referred to as noise. Now, it generally is not associated with the process, but is induced or picked up or conducted by the cabling or the various associated equipment along the same cable, which will then superimpose itself as a signal going into the controller. Now, because the controller or some controllers don't know the difference between an actual signal or the process signal and the noise, they create instability. Okay, so one of the techniques that is prevalent is try to reduce the amount of that noise. Okay, so to get a good visual indication of the type of signal that comes into it, there are many different tools that you can use. One of the most useful tools, especially in field checking, is an oscilloscope, and the oscilloscope does actually give you a good waveform check of the particular system. This is a cathode ray oscilloscope. These have been superseded by liquid crystal displays, but they give you the same type of trace. Okay, in other words, they actually look at one signal, say for instance a DC voltage, compared to a voltage that's coming out of a sensor. Okay, so a few ways to actually reduce the effect of noise is firstly through filtering. Okay, either using a electronic conversion into the digital realm, in other words, conversion from an analog into a digital signal, and then doing noise filtering based upon frequencies. Okay, and whether you have, or you could actually use a analog frequency suppression, which is obviously what a filter is, and there are various types of filters that will give you different types of signals which minimize the actual induced non-process related noise. Okay, so so you have something like a PV filter. Okay, so now you can have noise filters, which filter out the actual noise, and they tend to be ones that have a fairly low threshold frequency. Okay, so typically they are a low pass filter. So and that's where you tend to have fairly low low smoothing objects or low smoothing things, but obviously that has to be looked at in terms of what your process is, because you don't want the filter to actually reduce the effectiveness of the actual controller, so there has to be some point there. There are ones that will actually give you a high frequency filter, so what they tend to do is give you isolate the frequency that is the of the noise itself, and then do through noise suppression, okay, invert that back into the signal, and hence put that as an antiphase or an inversion, and that creates back into the signal, which then cancels out the noise and just leaves you with a very, well, a lot cleaner signal. Okay, so that's filtering is one of those issues to make sure that the stability and the accuracy of the signal going into the controller mimics or is analogous to the actual process. Okay, now there are many different types of noise, as I mentioned before, and they could include the actual process or the measurements, okay, which includes the electronics, the cabling, etc. So each one of those needs to have a specific type of filter. Okay. So so when we have a look at the filtering or the actual value, the idea is that we need to make sure that whatever we're put in to suppress erratic points of the signal, we have to make sure that it does suit the process. Now, firstly, we have to identify the actual noise, and as I mentioned earlier, that there are various sources of noise. But if we look back into classical control theory, then the noises are actually either the electrical noise, I should say, are based around three concepts. One is emitted radiation, one is conducted radiation, and the other one is electromagnetic induction. So you have electrostatic induction or electrostatic coupling, you have electromagnetic induction or conductive interference. So each one of those will give you a source of distortion, and they need to be looked at because they will create instability to the process, because it's giving the controller the need or the requirement of reacting to a lot higher frequency and also a lot different magnitude than the actual process. So in other words, it creates an error based upon the noise. Okay, so use the filtering with caution, and also check the parameters that are also put in for the tuning after you adjust the filtering. Okay, another way to not just mathematically put in a filtering, but also to do a physical filtering is to use shielding and or grounding the actual cabling, and also using noise suppression techniques such as common mode rejection. But each one of those will give you the reduction of the noise, which will give you the closer relationship to the real process and the signal that you're coming in. Okay, thank you.